Hello, stats students. Welcome back. Today we're going to start section 10.2. We're going to start looking at comparing two means. So in 10.1 we were comparing two proportions. Now we're going to be comparing two means in 10.2. And we're going to start with, this first objective here today. But first, let's talk about 10.2. In a previous section, we developed methods for comparing two proportions, like I said, but what if we wanted to compare the mean of some quantitative variable for two populations? So the parameters we're interested in now are mu1 and mu2, those are means. And once again, the same idea as the best approach is to take separate random samples from each and to compare those sample means. But suppose we want to compare the average effectiveness of two treatments. This is different than studying two populations. So we could do a completely randomized experiment. The parameters are mu1 and mu2, and those, in this case, are the true mean responses to the two different treatments, respectively. And then we use the mean responses in our two, sample groups to make the comparison. So basically, here's the idea. We've got either two populations or two treatments. There's some parameter. We're trying to study the relationship between these two parameters. And to do that, we study these two statistics. And we might have, different sample sizes there. Before we get too into it, if we were in class, we would have done an activity today. Instead, I'll just kind of talk through what that activity would look like. How quickly do synthetic fabrics such as polyester decay in landfills? So a researcher buried polyester strips in the soil for different lengths of time and then dug them up and then measured the force required to break them, because that's an easy way to measure, or an easy thing to measure, and it's a good indicator of decay. Lower strength means more decay. So the researcher buried 10 strips. They were assigned to two groups randomly. 5 of them were buried underground for 2 weeks. The other 5 were buried for 16 weeks. And then they measured the breaking strength of each strip after they were dug up. So you can see group 1 was underground for 2 weeks. Here are the breaking strengths. Group 2, 16 weeks. And again, a lower strength means the fabric has decayed more. So does this data give good evidence that polyester decays more in 16 weeks than 2 weeks? Well, let's take a look at what the graph of this data looks like. So you can see in group 2, much more variability. Group 1, much less variability. However, you also want to look at the center, like where are these 5 centers? Maybe like somewhere in here, where this is a slightly higher center. And we can actually calculate and compare their means. Group 1 has a mean of 123.8. Group 2 has a mean of 116.4. That's a difference of 7.4 pounds. So is it plausible that this difference is just because of chance involved in the random assignment and that the two treatments themselves didn't do anything? Well, to find out, we're going to do a simulation. Now, to do this simulation, we're going to suppose that the length of time in which it was in the ground had no effect on the breaking strength. So basically, each one of these specimens, this is how, what its breaking strength will be no matter which group it is assigned to. So basically, we take these 10 strips and we randomly assign them to either group 1 or group 2, and we just assume they're going to have the same breaking strength. So we would have written the 10 strips or 10 breaking strengths on the index cards and just shuffled them and dealt 2 piles of 5. We would have calculated the mean of each group and then found the difference and recorded that value. Each of us would have, run this simulation many times and made a dot plot of our breaking strength differences. Luckily for us, I have some data here from a past year where the class did this. And you can see here are all the differences that they got. Then you can see the number I've highlighted here is 7.4 because I want to know how often did the difference in this group, exceed the one we found in the study. And you can see that I counted up 16 times out of 102, which is about 15 or almost 16% of the time. Now again, this number right here is basically a p-value. It's the area under the curve to the right of this value that we got in our actual sample when they actually did this experiment. So this is the chances of getting a value this extreme or more extreme, assuming the treatments don't make a difference. So what conclusion can we draw using this probability right here? Well, that probability of 15 or 16% is definitely more than the usual 5%, which means that it's, you know, it's not really that rare if you're just randomly assigning them and the treatments don't make a difference. So do we have convincing evidence that it decays when left in the ground for long periods of time? And the answer would be no, we don't have convincing evidence, because we, based on this, would fail to reject the null hypothesis and can't conclude this alternative based on the evidence that we have. So this is an example of comparing two means using a simulation. What we're going to really dive into in this section is not just relying on a simulation, but using the sampling distribution of the difference between two means. And that's what we're going to start looking at right now. And this will, of course, be related back to what we studied in Chapter 7 when we studied sampling distributions. Here's what we know about the sampling distribution of a mean. Its shape is approximately normal if n is greater than or equal to 30. It's centered at the true mean. And the formula for the standard deviation is sigma divided by the square root of n. And again, if that 10% condition is true. So to explore the sampling distribution of the difference, so if we're finding, the difference of two means, we're going to start with two normally distributed populations where we know the mean and standard deviation. So we're going to look at the heights of 10-year-old girls and the heights of 10-year-old boys. And 10-year-old girls' heights have a normal distribution centered at 56.4 with a standard deviation of 2.7. 10-year-old boys, normal distribution centered at 55.7 with standard deviation of 3.8, and those are all in inches. Let's say we take independent random samples of 12 girls and 8 boys that are all 10 years old, and we measure their heights. So what can we say about the difference between, the mean of the female heights minus the mean of the male heights? So we can simulate this. We repeated this 1,000 times and we got the following. So let's take a closer look here. Here are the mean each time when we sample 12 females of age 10. You can see these are all the different means that I got. The center of all these means is 56.4, and the standard deviation is exactly what we'd expect, 0.78, using that formula. For boys, the mean is 55.7, and still a slightly larger standard deviation, as we expect. Then if we take the difference, so, if I take one of these, let's say that one was the one I got this time, and subtract that one to find it's different, I get one of these values. And you can see that this is basically the approximate sampling distribution of the differences, which is centered at 0.7 with a standard deviation of 1.55. And 0.7, you can see, is, exactly the true difference between the parameters. So basically, it follows this rule that we'd expect. And this is a rule we learned in Chapter 6 about independent random variables, is that the mean of the difference of two random variables will be equal to the mean of the first one minus the mean of the second one. So that is not a surprise. Remember, though, for the standard deviation, you cannot add the standard deviations. You have to add the variances. Even though we're finding the difference of two random variables, you add the variances. So if I plug in the formulas for variance for group 1 and group 2, I square both of them, and I get the following. This should be a 2 right there. And then there's my formula to find the standard deviation of the difference of two sample means. So, putting that all together, here's what we know about the sampling distribution of the difference between sample means. So if we choose an SRS from population 1 and a separate SRS from population 2, the shape will be normal if the populations are normal. In other cases, it will be normal if both of the sample sizes are at least 30. So either, both populations are already normal, or if both sample sizes are at least 30. The center will be centered at mu1 minus mu2, and then the standard deviation will follow this formula right here. And again, as long as the 10% condition is met. So then here's a picture of that same information. This is what we'd expect the sampling distribution of a difference between two means to look like. Normal distribution, again, if the populations are both normal or if the sample sizes are at least 30. There's the formula for standard deviation, and we'd expect it to be centered at that mean. So let's take a look at an example here. So we take those samples, we analyze the data, and the researcher reports that the sample mean of the boys is actually larger than the sample mean height of the girls. So describe the shape, center, and spread of the sampling distribution. So it's centered is normal because both population distributions are normal. The mean is going to be at the difference of those, like we said, and we can find the standard deviation by plugging these four values, 56.4, 2.7, 57, 55.7, and 3.8 into the formula here, along with the sample sizes of 12 and 8, to get that the standard deviation would be 1.55. So you can see here's the normal distribution centered at 0.7 with a standard deviation of 1.55. So that's one standard deviation away is 1.55 inches above the center. Next, let's look at the probability of getting a difference of sample means that is less than 0, because that would mean that the boys' mean height was larger than the girls' mean height. So you can see that 0 would be like right here, and I want to find the probability of getting a value less than 0, so I'm going to try to find that area. And, you know, like we've done so many times, we use the normal distribution. You can find the z value and use table A, or you could use normal CDF, you know, using this center and this standard deviation to find the area below 0. And you would get that the area is 0.3264. So do these results give us reason to doubt the researchers' stated results? Well, a 33% chance that you would just get a result due to sampling variability. That's not very rare. That's not a really small number. So that gives us little reason to doubt the researchers' claim that that's actually what they got. So that's where we're going to stop for today. We learned about sampling distributions for the difference between sampling means, and we basically did probabilities using sampling distribution, the difference between two sample means. Going forward tomorrow, we'll start looking at conditions and how to do actually, you know, confidence intervals and significance tests later on.